project is based on the muscle contraction. So a muscle consists of bundles of microfibers. Each muscle fiber is a cell that contains many myofibrils. Each myofibril contains actin and myosin filaments. Myosin and actin filaments are actually tiny force-producing engines. During a muscle contraction, myosin filaments form cross bridges with actin filaments. The cross bridges then change shape, pulling the filaments toward the center of the sarcomere. To be more exact, our project explains the sliding filament model. When a muscle is relaxed, myosin and actin filaments are not attached. During contraction, myosin attaches to binding sites on actin, forming cross bridges. Using ATP, the cross bridges pull the actin toward the center of the sarcomere. The cross bridges break myosin binds to another site, and the cycle begins again until the muscle is contracted. The chemistry behind muscle contraction is simple. A message travels from the nervous system to the muscular system, triggering chemical reactions. The chemical reactions lead to the muscle's fibers reorganizing themselves in a way that shortens the muscle, that's the contraction. When the nervous system signals is no longer present, the chemical process reverses and the muscle fibers rearrange again and the muscle relaxes. The release of ACH is extremely important. A muscle contracts until the release of ACH stops, and an enzyme produced at the axon terminal destroys any remaining ACH. Then the muscle cell pumps calcium 2+ back into storage, and the cross bridges stop forming and the contraction ends. The two main elements present are calcium and sodium. The sodium influx also sends messages within the muscle fiber to trigger the release of stored calcium ions, while the calcium ions diffuse into the muscle fiber.
This is the model. It is not complete already, but it worked like this. Well, here, this is the muscle contraction. This represents the muscle when it is contracted. And when we separate it, like this, represent the muscle relation. This is the myofibrils. This is the C line. The M lines are there. And this is the actin.
What I did for this STEM project stage was to paint the redwood parts that will represent the M and C lines that in real muscle contraction react with myosin to produce the different movements of the muscles.
What I did in this experiment was to paint the straws of red and put in each of them a pipe cleaner of yellow color that represent the myosin.
During a muscle contraction, myosin filaments form cross bridges with actin filaments. The tightly packed filament bundles are called myofibrils, Each myofibril contains thick filaments of a protein called myosin. On our sarcomere, I made the myosin heads with foamy, and these myosin heads act in the model as tiny force-producing engines.
Muscle contraction is stimulated by the motor neuron, and then some electrical signals activate the sarcoplasmic organelles called crosslinks in the muscle cell. The myosin heads that are highly polar cross the space between the myosin and the actin and attach to the highly polar sites on the actin binding. And when the muscle relaxes, the nerve ending ceases to supply sarcolemma.
Our project and it isn't ready yet, but I think we can make change to measure it and to get a better job to represent the contraction and the relaxation of the muscles. And I think we make a good job in this part of the project.